So good evening and welcome to this session on mechanical principles, unit 8. So we're going to look tonight at assignment number 4. Now usually we do these in 2 parts, but looking at assignment 4, it's really not necessary to do it in 2 parts. We'll do it in 1 part. So that means there won't be another session to accompany a session assignment 4. So no more to do, let's make a move, let's make a start. So let's just have a quick look at the assessment criteria for assignment 4. So we've got P9, which explain the natural frequency of vibration in a mass spring system. And we'll move forward to M4, which to determine the amplitude and the phase angle of the transient response within a mass spring damper system. So we'll look at dampers. And the last part, which is the distinction part, is to identify the conditions needed for mechanical resonance and measures that are taken from preventing this from occurring. So we'll look at those preventions as well. So the way we're going to approach this is that I won't be doing any examples because otherwise I'd end up doing the assignment for you, but we'll try and point you in the right direction so that you know what to do to complete each of the tasks in assignment 4. So starting off with assignment task 1, we'll discuss the background theory first, and then we'll think about an approach to answering task 1. Then we'll review the theory and prepare you for task 2. So the theory of task 1 and task 2 are very closely linked. So they feed one into the other. So that should be good preparation for task 2. And then the last bit is we'll discuss the concept of vibration resonance. And that, of course, is relating to task 3 of this assignment. So we'll start off with some theory, some background theory. Now, this may look sort of quite daunting, but it isn't. The first thing is you're asked to define simple harmonic motion. So what we'll do is that we'll go through the definition of simple harmonic motion. So a particle is said to be under simple harmonic motion if its acceleration along a line is directly proportional to its displacement from a fixed point on that same line. So what that means, if we have a look at this image here, we have a point C. It says the displacement of that point is directly proportional to the acceleration. So the greater the displacement, the greater the acceleration is going to be. So that's all the definition of simple harmonic motion. So what we're going to do, we're going to consider the motion of particle A, so particle A on that image, rotating in the circle with a constant angular velocity omega. So we have this part A is rotating around that path in a circular motion. That's point A, and point C is its position on the vertical axis. So that's point C there. And we're looking at that motion of point C from zero displacement to the maximum displacement in the vertical direction. And then we'll have the maximum displacement in the negative direction. So the first thing that we want to look at is the period. Now the period time of any cycle is the time that it takes to complete one cycle. So one revolution, if you like, of particle A. And simply the period time t is 2 pi over omega. That's fairly straightforward, isn't it? The other thing that we're interested in is the frequency of rotation. Now the frequency is in hertz or cycles per second, and it's simply 1 over the period, over the time period for one cycle. So then we can say the frequency is therefore equal to omega over 2 pi. So it's the inverse of what we had up here, the time period. Now, if you look through your notes, what you'll find is that there's a derivation of this equation that I'm highlighting now, where the acceleration of particle AC, so that's the acceleration of point C up and down that y-axis, is equal to minus omega squared times the displacement yc. So what that tells us is that the acceleration is directly proportional to the displacement. Yeah, so the greater the displacement, the greater the acceleration. And that's the definition of simple harmonic motion. So I'll read this last paragraph. It says, this equation shows that the acceleration AC along the y-axis is directly proportional to the displacement yc along this line, and therefore point C is moving with simple harmonic motion. So one of the first parts of task 1 is to define what simple harmonic motion is. So if you can pick the bones from that, then you will have done an excellent job answering that question. Right, we're going to just move on now, taking some of the equations that have been developed in this part here on this slide, and we're going to move over to the next system, which is a spring mass system. Notice I've put the words no damping in there. That's never going to be the case. There's always damping present. So if we pull a spring down with a mass on it, we pull the mass down, let it go, it's going to oscillate up and down, but eventually those oscillations will die down, and that's because there's some damping. It could be air resistance, but most of it is in the actual spring itself. So there is always going to be damping, but for theoretical case, we're going to assume there's no damping. So if we have a mass hanging on a spring and we displace that mass and let it go, it's just going to oscillate up and down, and it's going to carry on doing that until we stop it. But anyway, let's look at the forces applied. So what we have, if we first of all look, if we just hang the weight on the spring, you would expect it's going to deflect. So we hang the weight on that spring and it's going to deflect by a distance y0 until it gets to this equilibrium position. So we haven't done anything, we haven't pulled it, we haven't disturbed it. All we've done is put the mass, hung the mass off that spring. So it's going to deflect, and you can appreciate that, I think. So if we look at the forces applying when it's in this equilibrium position, then the force up is the spring stiffness K times that displacement, because the force, the spring stiffness is a function of the force times the displacement. So it's K times y0, spring stiffness times the displacement, and pulling it down is due to the weight of the actual mass, and that force acting down is mg. So when it's in the equilibrium position, there's no disturbance, then spring stiffness times yo is equal to mg, and it's stationary, it's in an equilibrium position. If we now pull this mass down, so we pull it down with our hand, and we increase the displacement from y0, and we add a displacement y to that. So this time the force is acting on our mass. The force up is still the spring stiffness, but this time it's the total deflection, which is y0 plus y. And the force acting down is mg. Now, if we pull it down, it's not in equilibrium, because if we let go, it's going to bounce back up and start oscillating. So it's not in equilibrium, it's actually going to accelerate up. So if we look at the net force acting on it when it has been displaced, the net force is mg acting downwards minus k times the total deflection, which is y0 plus y. And that must equal the mass times the acceleration. And it's going to accelerate up from that point. Now we can rearrange that a little bit by multiplying out this bracket. So we get the force is equal to mg minus ky0 minus ky, and that's equal to ma. So no changes, just multiplying these brackets out. However, we know that ky0 is equal to mg. That's the equilibrium position that we started from. So that means we can substitute now 4ky0 into this equation here. So we can replace ky0 with mg, and it's going to be minus mg. So we have mg, force is equal to mg minus mg, so they cancel out, minus ky is equal to ma. So we forget about the force, so we end up with minus ky is equal to ma, and rearranging that we get mass times acceleration plus the spring stiffness times the deflection is equal to 0. Could rearrange that by dividing throughout by m, so we get the acceleration is equal to minus k over m times the deflection y. Now you've seen this equation before on the previous page, where we had acceleration is equal to minus omega squared yc on the previous page. So that means we can say that k over m is equal to omega squared. So taking that forward, we have omega squared is equal to k over m. So omega is equal to the square root of k over m. Now it's starting to become a useful equation now. Going back to the previous slide, we remember that the time period t is 2 pi over omega. So we're going to substitute now this omega into that equation. So we're going to replace this omega here with the square root of k over m. And if we tidy that up a little bit, it means we can take the square root to the top, and we have to invert the value of k and m. So it becomes m over k. So the time period is equal to 2 pi square root of m over k. Now that's a very useful equation for what we're going to do next. Just to remind you that the frequency was 1 over t. And because there's no damping in this system, what happens when we pull that weight down and let it go, it's going to oscillate at a certain frequency, and it'll carry on like that because there's no damping in there. If we haven't got any damping, that is known as the natural frequency of the system. And that will carry on indefinitely until we stop it. And that's known as the natural frequency of vibration for a spring mass system. Now, if we had this system placed horizontally, that expression is exactly the same, provided there's no friction between the mass and the surface it was sitting on. So taking that one step forward, we know the natural frequency is 1 over t. We know the time period t is 2 pi square root of m over k. So we can rearrange that equation that the natural frequency is equal to omega over 2 pi. We've done that before. And that's equal to 1 over 2 pi this time times the square root of k over m. Yeah, so that's our expression for a natural frequency. So notice in that equation what we have the value of k, which is the spring stiffness, and we have the mass of the vibrating system, our hanging mass here. Right, so coming back to task 1, what you're asked to do for a free oscillating mass spring system, define what is meant by simple harmonic motion. And I think we've done that so far, so you should be able to define simple harmonic motion. Don't expect you to derive the equations or anything, but just say what it is and maybe include the equation for simple harmonic motion. Define the natural frequency of the system. So the natural frequency is the oscillations when there's no damping, and that's given by our expression down here. So you can define the natural frequency from the work that we've just done. So part C of that question was explain using appropriate equations what properties of the system could be altered to change the natural frequency. Stating whether these property changes increase or decrease the natural frequency. That should be Fn, by the way. I made an error there. So let's just change that. So that should be Fn. So what we have our natural frequency equation, and the question is asking, what properties can we change in our system to change the natural frequency? Well, we've only got two properties. We've got the spring stiffness and the mass. So if we increase the spring stiffness, then the natural frequency is going to go up. So you can change the natural frequency of a system by changing its stiffness. Or you can change the natural frequency by changing the mass of the system. And they're the fundamentals of looking at vibration analysis. You can control the natural frequency of a system by changing its mass or its stiffness. Yeah, so there are many examples where that occurs in real life. We'll talk about them a little bit later. So let's move on to task 2. This is a bit more involved. Again, take your time, and hopefully if you've got any questions about this, ask about them at the end when we stop the recording, and we'll go through them again if you want to. So what we have a mass of 1.5 kilograms is attached to a vertical spring as shown in figure 1. Yeah, below. So done what you should put in your assignments as shown in figure 1 below. So I know what I'm talking about now, that figure. So try and put that in your assignments, please. Those little statements are quite important. So when the mass is displaced downwards by 55 millimeters from its position of rest, so from its equilibrium position, it's observed to oscillate 60 times in 72 seconds. Determine the periodic time, T. So you can get the periodic time is simply 72 divided by 60, isn't it? So it'll be 1 point something seconds will be the periodic time. The second part was to determine the stiffness of the spring, K. Now, if we've got the periodic time here, we've got the mass. Let's just tick them. What information have we got? Just choose a pen. So look at the equations that we've got available. We've got the periodic time T. We've got the mass. So we can calculate K. So we haven't got that, but we can calculate K from that expression. We're then asked to determine the angular velocity omega. Again, you've got the periodic time. You'll also have mass and K, so you can go from either end, you can work out the omega value, the angular velocity. So that's relatively straightforward. Now this is where it gets a bit messy, so you'll have to bear with me. I've got some slides that I need to refer to help us answer this question. So it's asking for the time taken to travel upwards a distance of 25 millimeters for the first time. It's important. And don't forget, and I've put in brackets, don't forget to include the phase angle due to the starting point. Now I'll explain what that is in a moment. So let's go over to the next slide. And you'll see we've got some displacement plots there. So displacement is a sine wave. So we've got displacement. These are displacement curves. So we've got two displacement curves there showing. I haven't done the velocity, the acceleration, but they're the equations for velocity and acceleration. They're derived in the notes, but I don't expect you to derive them, but I do want you to use them properly. So the displacement Y is R, and R is the amplitude. In this question too, it's 55 millimeters. We've got sine omega t. You'll have omega, but you won't have t because that's part of the question. And then you've got this displacement or phase angle. You've got the phase angle phi. So graph is a plot. The first one, the dark blue one, is a plot of R sine omega t. Yeah, so there's no phase shift in that first sine wave. So that's how the displacement's going to vary with time. The yellow line is that has some displacement. I haven't said what it is at the moment, but what we've done is I've applied some phase shift, and then they're in radians. And you can see that the start point is different. And all it means is that this sine wave has shifted along by that phase difference. Yeah, so just bear that in mind. So as R is the amplitude, omega is the rotational velocity or angular velocity, t is the time, and phi is the phase shift, and that's in radians. Okay, so there's an example in the workbook that you can look at. So if we turn the page, the problem that we have is that the starting point is with maximum deflection. So if we go back to the question, you can see that the start point is when R is 55 millimeters. That's meters, it'd be millimeters. Just say millimeters in the question. So you pulled it down 55 millimeters and you want to find the time it takes to travel upwards from when you've displaced it by 55 millimeters to go up by 25 millimeters. So that means we've got to add a phase shift into there because of the start point is being at the deflection when the deflection is 55 millimeters. So all you have to do is that actually equates to a 90-degree phase shift, which is pi over 2 in radians. So our displacement curve would be y, that's the displacement, is r, which is the amplitude, times sine omega t minus pi over 2. And what that does, when time is naught, then the displacement would be the 55 millimeters in your case. This is a different example, but that's the displacement at when you'd let go of the actual mass. So it is displaced. Otherwise, it wouldn't move, was it, if you didn't displace it? So you've got to add a phase shift in there to allow for the start time being with a maximum displacement. So on this particular slide, I've plotted the velocity profile and the acceleration profile. Now, can you remember what it said is for simple harmonic motion to occur, then the acceleration is directly proportional to the acceleration. So when we have maximum displacement, look at the acceleration. We also have maximum acceleration. And when we have no displacement, such as in this point here now, then we shouldn't have any acceleration because there's no displacement. And true to form, we have no acceleration. And it's the other way around, if you remember, because it's the acceleration is minus omega squared y, y being the displacement. So it's opposite in sign value, but they're directly proportional to each other. And the velocity is out of phase 180 degrees. That's from the example in the workbook, but you'll have the same issue with a phase shift for you on assignment 2 will also be minus pi by 2. Now we appreciate when you do this, it's very easy to make a mistake. And the important thing I want you to remember is that this y isn't the 25 millimeters. It's the distance from where there's no displacement. So your y value in your question will be 55 minus the 25. That would be your y value. Yeah, because it's the distance the displacement is from the 0. So you've already come up 25 millimeters. So your displacement, at the point that you want to find the time, will be 30 millimeters. So it's important to remember that. I do appreciate it's easy to make a mistake with this sort of assignment. If you make a mathematical error, it's not the end of the world. Providing the method's right, you're going to get essentially all the credits. Very rarely do we take something away for something that's complicated and relatively easy to make a mistake. Providing the method's right, you will get the credit for that assignment. Right, so I'm just going to move forward onto task 3. And task 3 requires you to explain in detail the conditions needed for mechanical resonance to occur and explain what measures could be taken to prevent resonance occurring. You will need to include the significance of damping. and I'll explain that to you. It is in the notes, but let's talk through it. So what I want you to think about, we've got a machine here shown as a square with it has a mass, of course, and it's on a spring system, and it has some sort of damping in there, and that's shown by a dashboard type damper. So there's a degree of damping in that system. We've got a mass, and on top of that mass, it could be a lump of concrete really with a rotating compressor on top, which is out of balance. So we've got a rotating mass here, which what we call is an out of balance machine, and that has a forcing frequency. Because it's out of balance, it's going to try and oscillate up and down. It has a forcing oscillation due to that out of balance acting on that system. Two things we need to know: there's that system will also have what's known as its natural frequency, and that won't change whether the machine's running or not. Actually, we can work out the natural frequency. It's simply the deflection of the spring when you apply the mass to it, and that will allow you to work out the natural frequency. But we don't want to do that at the moment. So just accept that that whole system will have some sort of natural frequency, and there'll be an out of balance force operating at some frequency. We call that FD as the disturbing force. Now think about these two things: the amplitude ratio. The amplitude of oscillation at a frequency over the static deflection. So it's how much this system is going to move up and down. So the amplitude ratio is a ratio of how much this system moves up and down. So it's going to move up and down with some amplitude compared to its static deflection when it's not running and just placed on the springs. So there's going to be an oscillation there. We refer to it as a damping, as an amplitude ratio. We also have this other factor called the frequency F of the driving force. Should be a D in there, shouldn't it? Of the driving force, FD. So that's the frequency of this driving force rotating out of balance machine. We don't know what it is at the moment, and we don't really want to know either at the moment. And that's the ratio of the driving frequency over the natural frequency of the system, which is Fn. Just remember those two: amplitude ratio, so it's how much this is going to move up and down compared to its static deflection when we just put it on the spring. And the other one is the frequency ratio, which is the frequency of the driving force, this here, that's FD, divided by the natural frequency of the system. Right, what that gives us, if we were to plot that with changing frequency, driving frequency, so if we have a system, we have a driving frequency FD, and we increase that, the natural frequency won't change, that's constant, but we can increase and decrease the driving frequency. So it could be a compressor, variable speed, out of balance load, so whatever it is, we can change the frequency of the driving out of balance force. So if we start off with a very low driving frequency compared to the natural frequency, so that means we'd be down here somewhere. And what we'd find with a very low, so this would be a low value of FD over Fn. Yep. And what we'd find is with those low driving frequencies, then the deflection or the amplitude would be exactly the same as the static deflection. So it wouldn't change very much. So it's fairly steady. It would go up and down with that frequency, and the amplitude ratio would be 1. If we now increase that driving frequency, so we speed up the machine on the top of that block. So what we're going to do, we're going to increase the speed here, increase FD. So we're going to increase that now. And what happens is we get to a point where the frequency ratio is FD is the same as the natural frequency. So that becomes 1. So when that's equal to 1, what you'll see is the amplitude ratio goes out of control. And that's what we call resonance. Now it's going to bounce all over the place. So the amplitude ratio goes off to infinity theoretically. However, you will see there are different plots on here. There's a blue, the purple and the yellow. They're dependent on the amount of damping that's in the system. So the greater the damping, the less the oscillations are going to be at the resonant frequency. So the resonance frequency occurs when the disturbing frequency is exactly the same as the natural frequency. That gives that causes resonance, that gives rise to resonance. And if you have no damping, then the amplitude ratio can go out of control and effectively goes off to infinity. But because you've got some damping in there, it's going to limit the amplitude ratio to hopefully within acceptable levels. You'd never want to operate a machine in this region where the frequency ratio is 1. So you try and make sure that you'd actually either well below the frequency ratio, well below a frequency ratio of 1, or well above a frequency ratio of 1 to avoid that resonance. And it's true, it does happen. If you know anybody been on board a ship, you'll see that there's a notice on the maneuvering panel of a ship's engine. There's a barring speed to avoid resonance of the propeller shaft. And what you have to do is you have to increase the speed of the engine quickly across this resonant zone and move into this part here to operate normally, to avoid the resonance occurring. So it's a real thing. It does happen. And it's quite common. You've probably come across resonance on a bus. And what happens on a bus, you know, if you've been at a bus stop and the side of the bus is bouncing, is vibrating away violently, what's happened is the side of the bus has a natural frequency, and it just happens to coincide with one of the natural frequencies within the engine. So you get a frequency ratio of 1, and that gives rise to resonance of the side of the bus, and that's why the side of the bus tends to vibrate more when it's at idling speed. Obviously not an ideal position to be in. If you rev the engine a little bit, all that resonance on the side of the bus would stop because you've increased the driving frequency. Right, so one example, and you're asked to give examples, practical examples. There's lots of them. If you go online, of bridges collapsing and all sorts. This is one example I've put on here. So I've asked the question, why do chimneys have spiral strakes? And I'm sure you've all seen chimneys like this with these spirals going up and down. Why are they there? You know, have you ever thought that? I hadn't till, you know, a few years ago. Well, the reason for them is that if that's our plan view of the chimney and we have a wind in a certain direction, at a certain velocity and certain Reynolds number, what will happen is as the flow goes around the cylinder or the chimney, what will happen is the boundary layer airflow will break away from the surface, and that will cause eddy currents to form. And what that does, depending which way it starts, an eddy current will give you a low pressure this side. So you could have a low pressure at this side there, but you'll still have a high pressure. So it could be low on that side and high on that side. What then will happen is, because it's high on this side, then you'll get separation starts to take place on this side and starts to form eddy currents, and the boundary layer will go back and touch the surface again. So now you have a low pressure on this side. And what happens is you get what they call vortex shedding off the back of the cylinder. And you'll see that they switch from one side to the other. And this is called a von Karman's street because he came up with a theory. But what happens, you have alternating high and low pressures, and then, you know, seconds later, it'll change to high that side and low to that side. And it keeps on swapping high to low, high to low. So you get low pressure, high pressure, low pressure, switching from side to side. And that, because of that, it tries to cause the chimney to move in both directions. Now, what happens is, if so happens that this vortex shedding pulsation happens to coincide with a natural frequency, so this chimney will have a natural frequency, Fn. And if this oscillating forces acting on it, which is again the driving frequency, acts on that chimney and it coincides with that natural frequency, then you'll get resonance take place. And actually chimneys have fallen down because of it, because of resonance of these pulsating eddy currents either side of the chimney. So what they do is to prevent that happening, if you put these spiral streaks around the chimney, that breaks up this profile because it's not uniform now up the length of the chimney. So you don't have the same pulsation frequency happening at the same point all the way at the length. It's going to be different at different points. So the risk of you having alternating disturbing frequency acting on the chimney to be the same as its natural frequency is taken away because it just won't happen. So that's why you have these spiral streaks on chimneys, is to prevent the natural frequency of the oscillations of eddy currents causing it to try and vibrate. Yeah, so that's sort of one example of where you can have problems of resonance occurring. Now, one of the end of that assignment, you've got to come up with some examples of resonance taking place in real life. There's numerous examples of soldiers marching over a bridge, and they put a sign up because if they all march together, that's at a certain frequency, and that can coincide with the natural frequency of the bridge, and it can resonate and fail. So on many bridges where you have soldiers potentially marching across, they'll actually put a sign, break step, so that they don't march, so you don't get that disturbing frequency. That's just one example. There's a bridge in America, I can't pronounce the name of it, but then they had wind blowing over the surface. You had these eddy currents forming, and that went into a resonant condition and it fell down. So there's lots of examples of resonance causing failure of systems. So you just need to describe one of those in the assignment. So just go back to the assignment before we finish. So undertake your own research to describe real world systems where mechanical resonance has caused problems and outline the measures that were taken to prevent it. Now, if you look at the equations, what you want to avoid is having a situation, so let's get back to the right slide. You want to avoid having the disturbing frequency being the same as the natural frequency. Now, if you can't do anything about the disturbing frequency, it might be an engine at a set speed. What you can do is change the natural frequency. And we know we can change the natural frequency by changing the stiffness of the spring support system or by changing the mass of the system. So I used to work in the shipyard, and one of the examples was that you had some vibration in deck panels, which just happened to have a natural frequency that coincided with the main engine, one of the disturbing frequencies in the main engine. So what was done to stop that resonance in those deck panels is that you just weld a bracket on, and that changes the stiffness, changes the mass as well. So you change the natural frequencies so they don't coincide. Right, so that finishes this session. So I don't want to go over this again, but don't forget what we need on your assignments when you complete the assignments. Include a contents page, identify each task, type it up, please, and equations can be handwritten. There are equations in this assignment, so please type them up. Handwrite equations, but scan them in using Microsoft Lens. Make sure they're neat. Put tables and charts in. Again, as I did in the example question, refer to the figures or the charts or the tables in the text so that they make sense. And include accurate citations and referencing. And you will be referencing information in this assignment. So make sure you have a look at them. So if you have any questions, we'll stop recording now. And then if you've got any questions,